Welcome everyone to our presentation on autoregressive conditional heteroscedasticity with estimates of the variance of UK inflation rates. In this paper, we revisit Robert F. Engle's conditional variance estimation model and apply it to more recent data. My name is Alexander Bellinger and I worked on this project together with Maximilian Pitilia. In this slide, I want to give you a brief introduction into the initial problem that Robert F. Engle faced. So when working with financial market data, evidence suggests that the assumption of homoscedasticity in our variables is not sufficient enough to carry out model estimation. As we can see in our figure on the left, there are time-dependent, or we can see time-dependent volatility clusters that capture the dependencies of our second moments of our variables. This leads to non-normal but leptokurtic distributions, which is characterized by the fact that they have a kurtosis above 3 and fatter tails on the side. So this next slide is relatively redundant, but for those who want to recall the properties of unconditional and conditional expectations and variances of basic AR1 processes, you guys can pause the video right here. But essentially what we're trying to say here is that unlike the conditional expectation of this process, the conditional variances is not time dependent. It is therefore that Engle introduced a model that let the conditional variances of a stochastic process be time-dependent, and he basically introduced the arch model, which managed to explain the differences in variances endogenously. So there have been models that explained the time-dependent changes in variances, but they always had exogenous drivers, which meant that they always needed to have a cause for the variance to change over time. So when building these models with lag-dependent variables, one can see that OLS estimates are still consistent, yet their standard errors aren't. And in order to find efficient estimates for our regression, we use the maximum likelihood estimation model. So to further specify our model, we use quarterly data from 2002 to 2018 on UK Consumer Price Index. As it is hard to measure changes in price inflation, we follow the assumption that price inflation follows wage increases. To get a constant real wage in the long run, we included the error correction mechanism of Davidson, which includes data on UK quarterly average wage earnings. So the model proposed by Engle, you can see in this slide where he observed typical seasonal behavior in PT-1, PT-4, and PT-5, which are the lags of quarterly consumer price index. So we denote WT or W as the logs of quarterly wage average earnings. We ran an unrestricted model from PT-1 until PT-6 and WT-1 and WT-6 and came to the conclusion that our data has the same typical seasonal behavior as Engle's model does. So we decided after doing exclusion restriction tests and making use of the Autoregressive information criteria that we would stick to the model that Engle proposed. When we examine the data, we can see by taking the logs of the first differences of our time series that we can visualize the volatility clustering going on within our data. When looking at the histogram, which is the figure below, of the first difference of the logarithms, we can see that our variables do not follow a normal distribution, as we observed a kurtosis of 3.501, which is above a kurtosis of 3, which is the standard kurtosis of a normal distribution. To test for serial correlation in the error terms, we made use of the Breisch-Godfrey Lagrange multiplier test and the Durbin-Watson t-statistic, and with both tests we barely found any evidence for serial correlation in the error terms, meaning that we can accept the hypothesis of observing purely white noise in our error terms. So when looking at our OLS results, we definitely see that our price correction mechanism is not significant with a t-statistic of 0.38, and we use the Autoregressive information criteria, and it's suggested for us to run a restricted model, which you can see on the right side. When you look at these results, you can see that there are strong opposite signs of our PT-4 and PT-5 long run coefficients, which is also observable in Engle's paper, and we also observe an unconditional variance of 0.00012827 within our OLS regression. To specify our arch model, we use the Lagrange multiplier test on autoregressive conditional heteroscedasticity and obtained a chi-square t statistic of 14.645 with 7 degrees of freedom, which is highly significant. So for us to satisfy the non-negativity and stationarity constraints, we used the model for conditional variances that was proposed by Engle, where we would only have to estimate two coefficients, alpha 0 and alpha 1. For us to do so, we worked with the assumption of a linearly decreasing set of weights of our past of our lags, and we therefore came up with the following model. When looking at our arch results, we see that our short-term coefficient has increased by about 6%, unlike in Engle's results where it dropped by about 50%. And what is also different from Engle's arch model is that our long-term coefficients have become more pronounced in either direction.
Using Stata, we found a conditional variance estimation model with coefficient alpha 0 equal to 7.75 times 10 to the power of minus 7, that is significant at the 5% level, and an alpha 1 coefficient of 0.6019, that is just not significant at the 5% level, but significant at the 10% level, for instance. It is interesting to see that Engle's original proposal for a declining set of weights for our lagged variables is a sufficient condition for a model to work at the 10% significance level. Next, we built a conditional variance estimation model for data prior to the financial crisis, where we had quarterly data from 2001 in the first quarter to 2008 the third quarter. We had 30 observations total. Therefore, we cannot fully work on the assumptions of the central limit theorem, and we chose the Akaike information criterion and the Schwarz information criterion still to select a specific restricted model over the unrestricted one or others. The Lagrange multiplier test on autoregressive conditional heteroscedasticity yields a chi-squared test statistics of 16.315 with 8 degrees of freedom. Stata tells us that there are arch disturbances present. The T-4 estimator now has a more pronounced influence on the predicted log of the quarterly consumer price index. However, in the conditional variance term, our constant is not significant at the 10% level anymore, and neither is our alpha 1 coefficient. This result needs further attention as we are still using quarterly data, and in the regression before, we have had significant alpha 1 and alpha 0 coefficients. So we decided to build a model on monthly data, as among possible explanations why alpha 1 and alpha 0 are not significant anymore is that we might have too few observations, or that the significant shocks in the time series in the given time frame are not visible at the frequency of the data, which is quarterly. Arch effects possibly vanish due to different temporal aggregation. To possibly capture the same seasonal behavior as in the prior model, we ran an unrestricted model with pt-1 to pt-12 as coefficients. The Akaike criterion led to a restricted model that we chose with lags for the 2nd, 3rd, 7th, and 10th month of the year. Performing an LM test showed that none of the first 20 lags have a significant chi-squared test statistic, meaning that this is not an arch process. To conclude what we have done, in the first model we managed to build a relatively precise model to predict one-step conditional variances on our entire dataset. Similar seasonal behavior can be observed as Engle did. However, nowadays distant past values of the squared error terms have a stronger relationship with today's conditional variances than Engle observed. Engle's assumption of linearly decreasing weights on past lags seems still satisfactory for our model to be significant at the 10% level. However, it is only significant at the 10% level and not at the 5% level. In the second model, we chose the same approach to choose a model. Stata did detect arch effects, but they were not significant. The model had only 30 observations, and we did not find any significant estimates for the conditional variance. Possibly these are the arch effects that are present vanished due to different temporal aggregation of the data than in the first model. Therefore, we tried to estimate a model with monthly data and hoped to get significant coefficients, but the result was also no evidence of arch effects detected. So to summarize again, initially we wanted to capture the same arch effects, yet just on another scale in the second model. But our obtained monthly regression model did not find any significance of the fourth quarter significant coefficients, let alone any sign of arch effects in the data. There are multiple reasons, such as that we might not have had sufficient information or data to observe the arch effects. We tried, by varying the frequency of our data, to be able to regress an arch model, so where arch effects existed, but it didn't happen. And we thought that if the arch effects exist, maybe we could have detected them, but we couldn't. Additionally, it is to be added that the assumption of a linearly declining set of weights we did not consider as a possible problem, as it is just a proposal and not an omnipresent application for capturing arch effects, but it still managed to work for the first regression on quarterly data.